where it should get a little less ductile, or really it just shouldn't change very much based on temperature. Aluminum is fairly resistant to this temperature change. We're doing a temperature change, but in this range that we're doing, which is room temperature, so about 20 degrees Celsius, down to liquid nitrogen, which is about negative 200 degrees Celsius. Aluminum is fairly consistent. In fact, this alloy of aluminum actually gets a little bit more ductile at the lower temperatures, but generally it's fairly consistent with aluminum. Now, cast iron also doesn't change very much. It is brittle at room temperature, and it is brittle when it's cold, so we're not really testing it when it's cold. The aluminum changes a little bit, the cast iron doesn't really change. It's already brittle. The steel, however, is the interesting one. The steel at room temperature is very ductile, but then as we get colder and colder, we get to something called the ductile to brittle transition point. All right? And what happens is that at room temperature, you'll have a ductile fracture, and then it transitions as the temperature lowers into a brittle fracture, or to a more brittle fracture in this case. More brittle than the ductile fracture. And so we're going to watch how steel at room temperature will be very ductile, and then as we drop the temperature, it'll become very brittle. That will be this one right here. So it starts, say, very high ductility and high energy impact. Obviously, if you're very ductile, you absorb a lot more energy, right? Rather than if you're brittle, because when you're brittle, especially impacts in general. So you'll see that it's a little different in other labs, but brittle materials like ceramics and other things, they're really hard. But if you drop them, they shatter, right? It's a very easy, very little amount of energy if you're impacting. So it's a specific type of failure, right? So for brittle materials, there would be a lot less energy required to actually fracture this. So you will see that we will use a lot less energy and a lot less time as well, because it won't bend as much. So that's what we're going to be looking at. I have some examples here of a material that is brittle. So I don't know if you've ever seen when you drop ceramic, it's kind of like a rough surface, but also very flat sort of thing. So this is what we're expecting. We're expecting a brittle fracture to be pretty straightforward, and it's going to be fast. There's not going to be almost any bending. You'll see a bit more bending on the aluminum side because it's a little bit more ductile, but it's not as ductile. And then it should just be a flat, simple break. Okay. However, this is aluminum, but this is not regular aluminum. This is almost pure aluminum. This is 99% aluminum. Right, so this is really soft. This is like really bendable. I don't know if you know, gold is also really soft when it's almost pure. So we don't use gold for structural things, but we use it for coating things. So this is aluminum. It's very soft. It's also extremely ductile. So you can see that it's bending instead. So this one didn't even break. Right? This one just absorbed a lot of the energy. So I don't know if you know, in a car, when you crash in a car, a lot of the stuff bends. And why is it important that it bends? It's important that it bends because it absorbs the energy from you. If it just cracked like this, your energy has to go somewhere else. So we will see that, right? We'll see that this absorbs very little energy, and then it will go to you instead, which is exactly what you're trying to avoid. So you put more ductile materials in the front, you want more bending, you want, what's the name of that? You have an open space, crumple zone. Right, so the crumple. So that's pretty much what's going on here. Okay, so that's what we're going to talk about. Any questions? It should be fairly straightforward. Like I said, we're going to do 5 samples here. So we're going to do 1 cast iron, 2 aluminums, 2 steels. We're going to get started by actually getting the liquid nitrogen here, because we need to let this sit for a while. Okay, then I'm going to demonstrate the machine. We'll talk about how we measure energy. Okay.
Go back to the point where you were saying about the ships. Wasn't